I just need to do like a bink over the 2021 and put 2022. Allison, good to see you here. Hunter, good to see you here. Dalen, good to see you here. All that cursed code. Oh my gosh. Check out last stream where Brian was like, just my code went crazy on the 475. But how's everyone doing? We're here to do some questions, do some work. Newbot is awake. He'll type back to you. Wait 1 second. Was it Allison said that? Wait. Here you go. It was Madeline. What are people working on? How are people doing? It's not me typing for Mewbot. Bring Mewbot out. Just chill out here on the stream. What questions do you have? It's been a busy day. Oh my gosh. So many things happening so quickly. Crashing code, craziness everywhere.
Mewbot is causing problems for Brian everywhere. Update, pretty radio buttons not responding because Mewbot is evil. Sorry, everybody. What's up, newspaper question? We'll need Brian for that. Mewbot does not know how to solve that.
Go away, Mewbot. Oh yeah, we got the newspaper question. Thank you, Lily, right here. Mewbot saying hey to everyone in the chat. So let's see, newspaper question. Oh, it's about the newspaper headlines, right? We made some really cool stuff. We made some Xbox buttons during 475. Xbox buttons, what? Let's go get that newspaper question. A newspaper tells a story about a ship. Just sit right back. You'll hear a tale. I don't know the rest of that song. Put your questions in the chat if you got them. We only have the newspaper question right now. So what are your questions? Statue 1, Chapter 19. Newspaper reports. Newspaper question. One more song here. Does the poll question require us to use outside? Which poll question? Which the poll question is that? Which poll question is that? Is it the political one? Jump makes things so much easier for this chapter. All the problems could be solved by hand, but using jump, it's gonna make your life really easy in this chapter. The gender and political party, I would highly suggest doing it in jump. Highly suggest. It can be done without jump. Just requires to solve down and find all expected counts, all cell chi-squareds, sum up the cell chi-squareds, find the degrees of freedom. That's a quick part. I don't know. We could do one by hand if people want. It's good practice. Just takes more time. We're doing the sunken ship question. Okay, newspaper headlines about a sunken ship. Gender and political party. And do you want us to do it without the resources? Do you want us to do it by hand or with jump? What shall we do? Let's do gender. Let's do sunken ship and gender. Here we go. Over to it. Let's check it out. So every time we're doing chapter 19, you've heard me say this tons of times for watching these videos, we're doing the relationship between what two types of variables? Chapter 19, chi-squared test of independence, is the relationship between two what variables? You see it up here? We're talking about the relationship between what two variables, like variable type. Identifiers, categorical, quantitative. We're talking about the relationship between two what variables with chi-squared test of independence. We're talking about... Yeah, we could do it the other way. If you want, Malin, just say, do it without jump. We'll solve the whole thing without jump. Which is good practice for the test. So, Malin, we could do that next. If you want, we could do that one next. No jump. Solve. Takes a little more time. Yeah, you can do it pretty quickly. So what kind of variables are we working with in chapter 19? The variable types we're working with are both variables are awesome. Let me put that on the list. Gender, political party, no jump. No jump podcast. So what kind of variables are we working with in chapter 19? No jump solve. Anyone know? No one knows what kind of variables we got. Alive or dead. That sounds like a certain type of variable. We've got male or female. That sounds like another type of variable. So what kind of variables is chapter 19 all about when we have a contingency table and a mosaic plot? If you have a contingency table and a mosaic plot, you are definitely dealing with what? You're dealing with what kind of variables? So if you are doing contingency tables and mosaic plots, you're dealing with what kinds of variables? So you're dealing with typical, oh no. Yeah, Statue 1 talks about like prostate cancer and ships crashing and baby abnormalities. Pearson just is all bright and shiny and happiness. So we're talking about two categorical variables right here. Two categorical variables. You've got, did someone live or die on the Titanic, and were they male or female on the Titanic? Now, the null hypothesis is easy for this because anytime we do the null, anytime you do the null, you're doing the chi-squared test of independence. So what word? Lily, great work right there. Lily, let's make you a mod. You're working with two categorical variables. And when you're doing the null hypothesis, you put what word by doing the chi-squared test of independence. Maria, good to see you here. Yeah, Maria, of course. So good to see you. Thank you, Maria. Everyone's being so nice. We're here to have a good time and relax. Thank you, Maria. What word do we put between these whenever we do the chi-squared test of independence? So the test literally tells you the name of the null hypothesis. You're doing the chi-squared test of independence. The null hypothesis is that living and your gender are independent of each other. So the null hypothesis would be that survival was independent of gender on the ship. The alternative being that there is an association means that they're not independent. So if things are associated, knowing someone's gender would give you information. So we're going to plot this out here in a second and see if we see some sort of association. Association means like your grade is associated with how much you study. Knowing how much you study would give you ideas of what someone's grade would be. With this, let's look right here. Are the conditions for inference satisfied? Well, the conditions are, you know them, you love them. Condition 1, random. Is it random? Maybe, kinda, I don't know. They don't go enough detail. They call this the independence right here, so they're using the independence assumption to talk about randomness. I wish we just said random. You know me, I love it. The next condition is less than 10%. Less than 10% of the observations are selected. There might be issues with that too, but they don't mention it. I wish they did. Random 10%. Now we pause. The next two conditions, because there's two in the last two chapters, are based on the type of data you're working with. So the third condition is going to be expected cell counts need to be all larger than 5. We can solve that out right here, and I want you to do this. This is a great practice if you're following along right now. Take right here this information and solve for me the smallest expected cell count. We're putting a 1,000-point bounty on this. What is the smallest expected cell count? 1,000-point bounty on this. What is the smallest expected cell count? The smallest expected cell count. How do we find expected cell counts? So we're just talking about how to find an expected, which is just, you know, how many females do I expect to die? Just happy topics from my Pearson today. How many females do I expect to live? These are the observed values, how many we actually see. Where when we say expect, it's like, well, if, let's say it's about 66% dead, well then how many we expect? Row total times column total over grand total. Great job, Madeline, right there. That's basically it. So let's solve for, great job, all 3,000 points, Madeline. Let's solve for this one. And why am I picking to solve for the females who were alive? Because females alive, notice, has the smallest row total and the smallest column total. So this is the smallest expected. So what do you get here, Madeline? What do you get when you solve this? It's row total times column total over grand total. Yep, and that's the way to check. Yep, exactly. And if this one's greater than 5, we pass on all of them. So there's the formula. Times those numbers together on top, divide by the grand total. And great work, Madeline. This is great practice. There you go. We're good. Great job, Madeline. We're throwing you another 1,000 points. Madeline, excellent work and great practice. Have you done the preterm pregnancy? We have. We can put it on the list, though, and do it again. So, Caitlin, stay tuned. We're going to do gender political party after this. But stay tuned. We'll do that one, too. Now, we're going to do one by hand here in a moment, but you would have to find all the expected, all the cell chi-squareds to do a lot of the work here. We're going to do it in jump for this problem, so watch how to do the jump work. Here we go. Click the box to copy your data. Copy to clipboard. Once you're here, I usually hit Control or Command-C just to make sure it's copied. So now that you've got it copied to your clipboard, you need to go and open up Jump. So go ahead and start opening up Jump right here, and as soon as you're inside of Jump, you can be anywhere inside of it. When you're inside of Jump, go up here to File, New Data Table. We're just going to open a new data table to put something inside of. It's kind of like a new Word document where we're going to put our data inside of it. So now that we've went to File, New Data Table, go ahead and click it. And once we go here, here's our new data table with nothing inside of it. With the new data table with nothing inside of it, we're going to go up to edit and then make sure to paste with column names. Now, don't click inside of it. I think that can cause issues. You should see paste with column names. Edit, paste with column names, because there was column names when we copied it. Once we paste with column names, you can see, and if you can't get it pasted, one person told me it doesn't have paste with column names, you could type these in manually. Like you could change the column name and you could type the data in to make it look like this. If you have it looking like this, we need to do one more step. So I'm going to pause right here. It's not really pausing, is it? Now we're going to go to tables and stack. With tables stack, we're going to take both those columns and put them on top of each other. So let's go here to tables and stack the blue ones. So make sure inside of here, double click them, that both of those blue quantitative columns are stacked on top of each other. Those represent the counts, and we're going to actually make this into two categorical variables with the counts of the observations for the frequency. Once you have this set up this way, you can click OK. Now here you are. This is what we want. You want to see two red variables for the categories, the alive females, and then the amount, which is the count. You've created count data, which is condition 4. So now we're going to go here to analyze. Claire, great to see you. We're going to go here to analyze fit y by x. And with the analyze fit y by x, this is going to look at the bivariate relationship. The whole point of this chapter is to look at the relationship between two categorical variables. And let's see if somebody's survival, which is that dashed variable, is explained by someone's label. So we have here somebody's survival, which is the label, is explained by this right here, which is their gender. We're going to put data in the frequency, so make it look like this, and you'll be good to go. Okay, we're almost there. Rage quit. Oh, no worries. I know, you should really see the last video, 475 class today. Things exploded. Whoa. What's going on right here? So there's females who survived, and here's males who survived. These are males who survived. Anyone notice anything? Maybe anyone see anything in this data? Talk to me about this data, which is kind of the end of this problem. Talk to me about this data. So talk to me about this data. Oh, it changes the stuff in the pretty options? Huh. So it sounds like we're close. Sounds like it's almost there. But don't worry about it. Don't spend all day on it. On the 475 mystery. Explain to me what's going on. These are males. And so everyone here is male. Everyone here is female. These are females who survived. These are males who survived. More dead males. Ah! That's the way the data goes. Welcome to the Titanic. 81.26% of males died. This is not historical data. It's similar as to the Titanic. They randomize it a little bit on it. We love randomness. So the chi-squared value is the 596.85. We're going to do one by hand here in a moment. Awesome, Dalen. 596.85, did I say? Good. 2 decimals. You're welcome, Dalen, anytime. P-value is 0. It's 0. This is... Let me just explain to you how 0 this is. This is a chi-squared with 1 degrees of freedom. It has 1 degrees of freedom because this is a 2 by 2. Degrees of freedom are rows minus 1 times columns minus 1. It's 1 degree of freedom. What is that? 596. So with 1 degrees of freedom, the chi-squared is very, very right skew. It looks like this. We're at 596. If you go all the way over here to like 9, well, wait, that's 9 degrees of freedom. If you go over here to 9, you're at almost 0 p-value. We're at 596. It's the applet won't even let, it's just saying you're ridiculous, which is fine. We like being ridiculous. It's so weird. It won't let you change it to that value. Yeah, their applet doesn't go that far. I don't know why. I guess they're just not doing any computations that far out. It's so far off the curve that it's basically impossible. So what are we saying? We're saying that the relationship we see in the data is basically impossible by random chance. That's what we're finding out. It's if someone told you, I don't know if there's an association between someone's gender on this ship and if they lived or died, you'd be like, okay, you try being male on this ship. And they say, nah, I prefer to be female on this ship. And you say, yes, because females had a higher probability of surviving. We saw that 77.8% of females survived as opposed to 18.74. They'd be like, oh yeah, that sounds like a very strong association. You say, yes, it is very, very statistically significant, i.e. we are going to what the null hypothesis. So what are we going to do to the null hypothesis right here, which is the last question? Remember, our null hypothesis is that the two things are independent of each other. So what are you going to do to that null? Your p-value was ridiculously low. How do we check extra points we have on Discord? Exclamation mark rank in the rank check channel. In the rank check. Make sure to do it in rank check. Not everyone's been doing it in random channels. We're going to reject the null. We're going to be like, that is... Think about that. Like, if your friend told you, just be like, let's not do stats for a second. You ready? If your friend said to you, I think someone's gender doesn't explain whether or not they lived or died on this ship. I don't think there's anything going on there. I don't think gender is associated with someone living or dying. I think there's no association. What would you say to your friend? Just talk to them like a normal person. They're like, I don't think gender played any role in whether someone lived or died. Like, if you just talk to them like a normal person, you'd say, I think you're wrong. I don't believe that. That's what we may say when we reject that. We don't believe this anymore. We think there's strong evidence of an association right here. So we have it via the low p-value, evidence against the null hypothesis. Our results go against what we should see. What rank do we need? The fifth rank. There's evidence to reject the null. There's evidence you're wrong, and the evidence is right here. This humongous gap right here, this big gap between the two, that difference in the conditional distributions is very evident. You don't just do it by looking at it. You're welcome, Priya, anytime. Great work, Priya. 100 points. Keep it up. And this p-value is 130 zeros. It's ridiculous. So, yes, we have insane evidence. Did I misclick any buttons today? I didn't click a button. Oh. We reject the null hypothesis. There is ridiculously strong evidence. I think I did the conditions right. Woo! We've have a streak since like mid last week, and we can't lose it. Can't lose it. Okay, we're going to do a problem by hand, which is great practice. So if you want to work some problems and make sure you understand how to do test-related stuff, let's check it out. We're going to do political party by hand. Let's check this out. So this is really good test practice here. It's going to take a moment. Try solving all these values with me. I'll probably repeat this when we start up the video right here. But it's really good practice just to understand how to solve these. Where is it? Political party. Here we go. Oof. This one's not even presented that well to you and how you'd have to solve it. Okay, so let's go do the political problem. We're working this one by hand. And it's going to take... Won't take that much longer. Here we go. Let's check it out. So this is the gender political party, and we are doing this version by hand, which is really good practice for the test. If you want to do it with Jump, please check out some of the other videos where I work it in Jump. It can be a little bit quicker, or if you remember how to do this in Jump like the other ones, check it out, give it a shot. So we first need to know what test we are doing. We're doing the chi-square test of independence, not the homogeneity. So chi-square test of independence, the null hypothesis is that X is independent of Y. Remember, you just put independent between these and basically say it. Someone's gender is independent of their political party. Do we see anything that resembles that? There it is. They just reversed it. You can reverse X and Y. Rock knows. It doesn't matter. You're so quiet, Rock. Am I going deaf? I hope not. And so we have gender, political party are independent of each other, and the alternative is basically the complement because they're either independent or we have evidence they're not independent. Count data is the condition that both variables are categorical. You're not doing chi-squared. You're not doing mosaic plots. You're not doing contingency tables if they are not. Great job, Adam, right there. Thank you, Adam, chime in. Adam, that's worth 1,000. Love it when people are following along right here in the chat. Adam, great work right there. Keep it up. Keep answering those questions. There's going to be a lot coming up right here as we practice how to solve this by hand. So count data means these are both categorical, and we can see that right here by looking at the graphic. If we're doing mosaic plots and contingency tables, we have to have two categorical variables. So that is a requirement. We have to have two categorical variables. We have it. That's a category. That's a category. What's your gender? What's your political party? Next, the randomization condition. Let's assume it. Be careful they switch to the yes and no position. I don't love it. We will check the expected cell count. I can tell you they're greater than 5. It's not because that's greater than 5. That is the current count. Great job, Madeline, right there. Keep it up. You know what? Madeline, 1,000 points. Love it if people are following along. We're just going crazy on points today. Tell people he's going crazy. He's lost his mind. He's giving out all the points. We'll have no more points left after this semester. So is the expected cell count frequency met? I got an expected. You might. There is one that you get like 3 on. Were you doing the one where you get that is the somebody's major. I'll show you how to get them here. This one is met, we'll solve it here in a second because we're actually going to have to solve all of them. Now we're into the point and the less than 10% condition. Okay. So now we're to the point where we actually have to solve and get these values. Okay. It's going to take a moment right here because we're going to have to actually add in a little bit of information to this. What do you notice between this current table where I can find expecteds and this table are we missing? Because we actually need these values and we don't currently have them. So what values are we missing? Oh, yeah. And then doing it in jumps quicker. And this is the full non-jump way to solving these problems. We're missing the totals. Adam on fire right there. You're right, Adam. We're missing those totals. And Madeline, too. So we're going to need to find the totals. Please tell me if I do something wrong in my head right here. This would be 85. Black. Is that right? This would be 78. This would be 42. And then across the top, 6, 31. Oh, my brain not working today. Brain is just not working. Can you do the number one with the birth order? Yeah, we can do birth order. You bet. I'm going to cheat. I'm going to use the calculator because I don't want to get anything wrong. Tell me if I get something wrong. Cheating. Calculator cheat time. 106. What else we got? What's the other one? Tell me if I get something wrong. 99. So here's a way to confirm the answers. Great job, Madeline. Excellent work. We have the totals now. To confirm your answer, that's 205 if you had this way. And then we should get 205 if we had the other way. We'll confirm answer. 205. Confirmation, if you add up the totals here and the other totals, they add up to 205. Because they both should add up the same way. These totals right here. This is the marginal display of somebody's political party. This is the marginal display of somebody's gender. And so those are the displays in the margins, so the total columns. Now that we have this information right here, we can go after we get the observed. Those are what you observe. And we can now find the expecteds. See if you can solve the expecteds for here before I find all the top ones. So find me the bottom row of the expected values. I'm going to start solving the top ones and showing how each value is solved. Every time we're doing it, we're doing row total times column total over grand total. And the way it works is you point in on the one you're solving for. So this formula right here, row total times column total over grand total, is pointing on that right there. Does that make sense? Like, if you think about it as arrows, it would go like this and like that, and that's the one it solves for when you do that row total, that column total, over the grand total always. So it's important to see that and know what we're solving for. So this is going to be 106, and this is how many males we would expect to be Democrat. That's 106 times 85 divided by 205, and we expect 43.95 males to be Democrats. So we expect 43.95 males to be Democrats. 43.95. It's a decimal. That's all right. It's just the way math works. Next, we need to take the next one to help me with the bottom row. So if you're working on this right now, solve me the bottom row. I might do the bottom row. If I don't have the answers from the chat yet, I'll solve it really quickly here. There we go. There's that. Notice how this points in on this, because that means we're solving for this one right here. So the values we are looking for are 78 times 106 divided by 205. That's, ooh, there was a typo. Shouldn't be that small. There we go. 40.33 or 40.33. Yeah, sorry. So 40.33. Okay, the next one. Oh, I meant to do my remove back time. Oh, that. There we go. Trying to keep it on there. And then we're doing this one here next, which means we go row total, column total over grand total. Someone got some answers? Yeah, I'd get to multicollinearity. When the x's share the variation, it's like which of these items look to have multicollinearity when you're baking a cake? Like the cake is the y side of the equation. Like the cake is the final product. Which of these, if you're baking a cake, would share multicollinearity? Flour, sugar, brown sugar, butter, cane sugar. Where's the multicollinearity in that cake baking? Flour, sugar, brown sugar, butter, cane sugar. Where's the multicollinearity, the shared variation in your x's, that they're bringing redundant information to the model? Like the x's within that conceptual idea right there that are bringing redundant information that are basically doing the same thing. All the sugars. And it's not that simple sometimes when we look at our x's, but the way we measure the shared variation is a metric of r squared sub I. So the r squared sub I is the metric of shared variation among the x's, because it's how is the ith x explained by the other x's. So you don't want to see a high r squared sub I. That's a bad thing conceptually. And we're doing the same equations. If anyone's wondering, I said I'd do the bottom row quickly. The bottom row, I'm just going to solve all them. 85 times 99 divided by 205, 41.05. We're doing one of these by hand. We're suffering through it. I'm going to move my contact around my 37.67. And now 42 times 99. It's just a lot of work. 20 point. Oh no, Madeline! We've done a lot of these problems right. This is good. Madeline, I'm 30,000 points. This is it's really good practice. If you do this a whole bunch of times, then you know how to use the equation. Madeline, don't worry. This is a great question. If I really thought it was a bad question, I wouldn't do it. I'd be like, let's not do it. It's good practice. This is making sure you know how to solve it. And if you do it a whole bunch of times, you get a lot of practice. It's just practice. And we need to make sure we know what to do next then. No, you're good. Good. No, it's just next question. What do we do now that we have the expecteds? Well, so I'll show you how to do this and jump here in a second too. What do we do now that we have all the expecteds? What do we do now that we have all the expecteds? If we now have all the expecteds, what do we do next? What is the next step? So we just found all the expecteds, and here I'll write the formula that we do next. Now that we have all, Kayla, you're so close, and Kayla, that's such good answers. Throw another 1,000 points. Kayla, you're right there, but we don't sum these. You're right there. We need to find the what's now. You're right there, Kayla. We're not gonna sum them yet, because these aren't the things we sum together. This was our solving for the expecteds. We don't sum the observed. You're super close. You're super close. We need to solve the name of this whole thing. We need to solve for each one of each cell chi-squared. So we don't have that yet, though. We only have the observed and the expected. So we took the totals right here, and we found the expecteds, because we first had to get these total things right here, the column totals and the row totals, and I guess technically the grand total being right here, we took the grand total. So then we were able to get the expected values. After we have the expected, we can then take every observed, which are these, and then we take every expecteds, which they have to be done with the respective one, take them, and the whole point of this is to find a cell chi-squared. And then we sum the cell chi-squares to get the chi-squared test statistic. So can anyone tell me how I will get the first value in this table? It's still a table. There's no totals in these tables. In the cell chi-squared table, what is the first value? These are all cell chi-squareds here. What is the first value in the cell chi-squared table? This value right here. I've got the numbers highlighted for you to use. So notice how we do the observed, which is how many male Democrats we see, versus how many we expect, divide it, and we square that. Once you get the difference, you square the difference, hence cell chi-squared. And then you take and divide by the expected to standardize it. So I'm trying to do it in my head right here to think what it's going to be close to check someone's answer. So 749. Okay, got it. So what are you getting? About 1.3? No, it's going to be smaller than 1.3. It's going to be about 1.16? 1.16? Oh, let's see if I can get 1,000 points on the line. Is it 1.09? Oh, it's too high. I was too high with that. That sounds about right, Caleb. Is it 1.1? Sounds close-ish. Let's find out the right answer here. Double check our work. We're going to take observed minus expected, and then square that difference, and then we divide by the expected. My brain's not working. And there it is. Oh, Kayla, you were right. It rounds to like 1.1. Yep. It was 1 point something. Okay, so that's 1.1 basically. And then we do the next one. So you're just going to permutate over here. So there's the next one right there. It's a good way of displaying it, I think. And so now it's 44 minus, you can subtract them either which way because we're just doing a difference. Is that 0.33, I think? Yeah, I remember that. There we go. Square this. Divide by the expected. Now don't forget to divide by the expected. There it is right there, 0.33. Oh, you got to carry all decimals probably. Like if you're doing this in the TI, carry all these decimals. Oh, I hope it's nice to us on decimals. 25 minus 21.72. If you do it this way and you get it off by a few decimals, just let me know. Like if you went through the trouble of solving all of this and it said you were off by 4/10 of a decimal or 3/10, just let me know. And I'll give you the points back. Because like, hey Brian, I solved it all by hand. I was off by 1/10 of a decimal. I say, okay, whatever. I say that's fine. We'll correct it. There we go. There's that one. Point. We're rounding it. We're in a dangerous game when we're rounding before our final answer. That's what you don't want to do. Brian's rounding before his final answer because his handwriting's big and messy. You can barely read that. That's a 5. 48 observed minus expected squared. That's familiar. And divide by 1.17 or 1.18. And then observed minus, oh, we got to move them so we can show what we're doing. We're just plugging in those values. Really? We're just plugging in those values and we're solving down here for the cell chi-squareds. These are the cell chi-squareds we're solving for. This value is these values you see here. These are the values we're using, the observed, the expected, and we're squaring it, just doing each of those values as it goes. So the observed is 34 in this instance. The expected is 37.67. Once again, this just finds a difference. We square the difference. We divide by the expected. I just do a thing a whole bunch of times. You get to practice at it. 0.36. Next but not least, and Kayla, what are we going to do when we find all these values right here? What do we do? Once you find all these values, the Pearson chi-squared test statistic, anyone can answer this. Madeline, Adam, anybody, Kayla. Once we find all these values right here, which are cell chi-squareds, we take the cell chi-squareds and we what them. So I'm finding the last cell chi-squared right here, which is about 0.5. There it is. So now that we have all the cell chi-squareds, every sum them up. Great job, Adam and Riley and Kayla. You know what to do. You take the sum of the cell chi-squareds. So now we take the sum of the cell chi-squareds. So we're just going to add all these up right here. You just sum them up. And those are cell chi-squareds. And so we're going to go right here. Plus 0.50, plus 0.33, plus 0.36. Don't make a typo. Plus 1.18, plus 1.11. There we go. It's 4. Wow, magic number right there, 4. So the question then becomes, now that we know the sum of all the cell chi-squareds, what do we do with this information, which is exactly 4, ironically. So now that we have the Pearson chi-squared test statistic, we should probably ask what about the chi-squared distribution we're working with. When we do the chi-squared distribution, we need to know it's what. Like when we find the Pearson chi-squared test statistic, which is, this is in the jump output, this is a totally different output, but we have the Pearson chi-squared test statistic. We have this now. What should I also know about it? What should I also know about the Pearson chi-squared test statistic that I'm computing? I should know it's this. Like the T, it also has this. We should know it's what? This is different output, but we just found for our test the Pearson chi-squared test statistic. We want to find the p-value, but we can't yet. The degrees of freedom, Adam, you got it. So to find the degrees of freedom here, we say, Brian, this is a 2 by 3. Notice how there was 2 levels to gender and there was 3 levels to political affiliation. So how many degrees of freedom are there? We're going to show how to solve this again. Remember, you say, Brian, this is a 2 by 3. It's a 2 by 3. And there are 2 degrees of freedom. And the way we solve that is we say if it's a 2 by 3, you drop each one by 1 and multiply them. It's rows times 1 times columns minus 1. And so it's a 2 by 3. There's 2 answers and there's 3 answers. Drop each one, multiply by 1. And so there's 2 degrees of freedom. The degrees of freedom, once again, tell us the shape of the chi-squared we're working with. So we're going to go over here to the chi-squared applet, enter in the 2 degrees of freedom, and it'll plot the chi-squared. We might actually have one up right now. We do. And so the degrees of freedom are 2. Watch the shape change. Boop. There it is. The more degrees of freedom, the more normal-esque it looks. Kind of like the t, but a little different. It's right skew. And we have here that the chi-squared value is 4, which means it's going to plot from right here over about 30%. No, oh, I did 5. There we go. 13.5%, which is slightly likely. Now, I'm worried. I want it, well, all that work, right? Oh, look. Look at this. 13.5 right here. Report the chi-squared to 3 decimals. Oh, man. I'm pretty sure it's going to get mad on us on this chi-squared. I'm pretty sure it's going to get mad on this chi-squared. 3 decimals. I could cheat and find it with R pretty well. I'm going to cheat a tiny bit. What is the P? Is it chi? No. What's the chi-squared? I don't know. Wait. Give me a half second. Where's the chi-squared? I don't do the chi-squared nearly enough on this. I could cheat with R too. Well, darn. It's going to get mad at me, isn't it? Well, what it is we would have needed to carry out all of our... This is why this one's just not fun to do by hand. And it's a ridiculous amount of work we'd never have you do on the test. If you do remember, I do this a lot slower. I don't want to get it wrong. I don't want to lose the streak. I was doing that problem about as fast. There we go. Don't want to lose the streak. Wait, there it is, 3.995. So there it is right there, 3.995. You think it would get mad at us? You think it's going to like say like, nope, 3.995? Let's see. That's the p-value. We found that. State the conclusion. The p-value is high. Just let the null fly. So we're going to fail to reject the null. There is not evidence right here. Check. I'll tell you. I knew it. When it says 3 decimals, watch that be right or wrong. There. Yeah. So what's its leeway on it? It's probably 3/10. No, is it, or 200ths? Whoo, that's a small leeway. That's why solving this one by hand is not advised. You need to carry out all your little tiny fractions. But once again, if you entered in 4, it didn't take 4. Yeah, it's got 200ths. No, that's 2,000ths. The leeway on this is plus or minus 2,000ths. If you entered in 4 and you got it wrong, just let me know. Yeah, just let me know if you got it wrong. Don't redo it. Like, hey, Brian, I was off by a couple thousandths. I'll be like, it's fine. I think we have 2 more problems at least, right? Someone said, what was the other one? What other problem was there? I should have wrote it down. Someone mentioned it. What problem? This was a really good practice right here, Madeline. What problem do people have right now? There was another one mentioned. Okay. Oh, wait, here it is. KLS. Let me go to the main screen. Here we go. Boop. Okay, so multicollinearity is an adjective to describe those x's that bring redundant information, or is multicollinearity a system stuff? Yeah, it's the idea. It's not the x's themselves. It's that there is multicollinearity with the x's. So it's to describe what's happening to your model. Your model has a lot of shared information in the x's. Does that make sense, Kayla? Your model has a lot of... we could do a little segment right here on what is multicollinearity. If you have a question, let me know. BS320, what is multicollinearity? CAD, great to see you here. Let's go talk over what is multicollinearity real briefly. So this might help or might not. We'll find out the hard way. To talk in the strict mathematical sense about what is multicollinearity, we have open questions right now. Let me know which ones you're working on. Does people say preterm? Someone might have went back and looked at that. Okay, so here's your x1 vector of information. Here's your x2. Does this make sense, Kayla, if you see it this way? Like, do you understand you're looking at like a data frame with your X variables? Does that make sense mathematically or just like visually speaking? It's just like a data frame inside of R. You go over here. Awesome. You go to like empty cars and then you click inside of here and you see the following. Really? There we go. So you see the vectors and we're just looking at vectors of data. It's just like an Excel spreadsheet with each row being an observation. So when you look at this right here, we're just going to put in different vectors. And we're going to put in the values now. We'll put in 1, 8, 3, 2, 4, 5. 2, 8, 9, 1, 4, 0. But look at this one. 1, 8, 3, 2, 4, 5. What do you notice about this data set now? I guess I could have made it inside of R. It might be even better if I do that. What do you notice? And actually, I'm going to probably do that. Think about this right here with the vectors. Let's actually make it inside of R because it's not that hard to make it. We're going to go here with the data frame. And the data frame we're creating has x1 equal to a concatenated vector of, sure, we go here. That's good. And then it has an x2 vector of concatenated. There we go. Set the right amount for the same length. And then it's a little obvious what I'm doing right here. Exactly. And there might be other degrees of multicollinearity. And let's put a y variable in. How many is this your correct data frame? That is, it's got 8 observations. Hey, what's up, Cole? Good to see you here. We'll do it this way. We'll do the sandwich approach. There we go. Sure. Trying to make my code look nicer. I don't know if I love that. Okay. So we're trying to predict y and unexpected parentheses close. Oh, comma. There we go. What? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, did I do 8? I did 8. I don't know how to count. Help me count, everybody. Okay. So this is our data frame. Does that make sense right here? Wait. Oh, Ryan, you had a question, right? Let me know your question, Ryan. What are you wondering about, Ryan? Feel free to ask. We can do it next right here. You got it. So, Kayla, does this make sense? We want to predict y. Where did you get the 3 point? That was the sum of all the cell chi-squares. That was the sum of all the cell chi-squares. For the previous problem, that was we summed up all the cell chi-squares by adding up all the values. So you have to add up all those values. My value in jumps is 406. Then that's the Pearson right there. Good work. If that's the Pearson chi-squared test statistic, and then the p-value will be 0 for that. The p-value for yours is going to be 0. If the Pearson chi-squared is 406, then the p-value is going to be 0. So with this right here, here's your y's and here's your x's. Now, what multicollinearity is not how the x's explain y. It's how the x's do what, Kayla? It's how the x's do y. It's not how the x's explain y, so ignore this first model right here. Multicollinearity is not how the x's explain y, explain each other, right? So if we go right here, we might reach a problem with infinity. We can't get parameter estimates on this one because there's 100% multicollinearity. And what is going on? Oh, library right class. And yep, there's alias coefficients. Let me change this to this. There we go. Cool. Okay, so I did. So yes. So that's all, Caleb, perfect theory, exactly. The problem I ran into with creation of this model is the x's were 100% redundant. So the x's, does that make sense, Caleb? The x's were 100% redundant previously, and I want you to look at x1 and x3 now. Notice that x1 and x3 are nearly perfectly redundant, like x1, x3, x1, x3, x1, x3. Does that make sense? They're almost perfectly redundant, except I had to make them not perfectly redundant. Does that make sense right there? They're almost perfectly redundant. like near perfect redundancy in what your x variable brings, x1 brings with your x3. Like they're almost identical. So this means it's like you got sugar and you got cane sugar. It's like, okay, this is basic. Someone says you want some sugar or some cane sugar in your coffee, and you're like, nah, it's about the same thing. Someone says you want sugar or you want dirt in your coffee. You're like, that's a very different choice. That's not the same thing. That's going to make a big deal. So what multicollinearity is telling us is that there is redundancy, and the model mathematically gets confused. Like what happens to the standard errors, as you said is true, is the model just doesn't know what to do. If you tell the model, do you want sugar and cane sugar? It's like, the model gets confused when you hand it things that are redundant, as in X1 and X3 are redundant in what they bring. And so the model just really doesn't know what to do mathematically. Like the mathematics turns out that way. And so the way to actually find the multicollinearity is to find this. We need to make a model predicting X1 from X2 and X3. Now, this is the model sub 1, we could say, because this is a model predicting our first X from the other X's. Does this make sense, Kayla? This is a model right here predicting our first X from the other X's. So the Y variable now is our first X, and the X's explaining it are the other X's in the model. So this is you could call it model sub 1 right here, because this is the model created explaining our first X from the other X's. Do we want this model to be really good, or do we not want this model to be really good? Remember, this is the first X being explained by the other X's already in the model, looking for the redundancy if the other X's can explain it. So when we run summary, we don't want, which one? Tell me which one, Ryan, and we can work that problem. Whether it be you might be doing the shipwreck problem, it sounds like, with the high chi-squared. Tell me which one it is. Yeah, let me know which one, and we can take a look right here. We don't want them to be explaining each other. So right here, we get an r squared. That's interesting. Oh, this one's good. Wait. That can't be right. Let me look at the VIF again. Something's odd. What? Which problem are you looking at, Ryan? Let me know which problem you're working on, and we can bring it up, and we can take a look. Something's odd, Kayla. Why is my X1 not being explained so well by my X3? It should be. Oh, do you see it, Kayla? There we go. I was looking at the wrong summary. I'm doing this right here so we can see a little bit more on this. Let's go. This is going to be ridiculous. Okay, cool. Does this make sense? We're now looking at this. Now, people might look at this and say, whoa, 99.85 r squared. But that means what, Kayla, interpretation-wise? 99.87, what does that mean? 99.85, what does that mean? Why are we like, no? And Ryan, put which problem you're working on. We can take a look at it here. Just be like, I'm working on the ship problem. I'm working on the gender political party problem. We can walk through the steps here next. Is this good or bad? And what does this mean for us, Kayla? Like, this means, like, how would you interpret that value? Correct. But is that good or bad? We've almost explained 100% of the variation. So think about what that means. Like, that's exactly right. It means almost nearly 100% of the variation in X1 is explained by the model. And what is the model? So like, oh, nearly 100% of the variation in X1 is explained, which means we basically totally understand it. We would basically know everything in X1 by knowing what? Like we basically... Exactly, and that means if we basically know everything in X1 by knowing X2 and X3, then X1... It doesn't matter! It's redundant information. And we see that here just in the data by looking at X1 and X3. X1 right here, this vector of information is basically identical. You can't always look at it so easily, and sometimes the idea of multicollinearity is that the other X's also share the variation because sometimes there's linear combinations. Why would exactly we don't, or maybe we should not use x3. One of them, we can see it here more visually with this. Multicollinearity can be harder to detect when it's like a lot of variables joining in to explain another variable, because the idea of multicollinearity is it's not just one variable that explains an x, it's like a combination of the other variables, which goes to like if you have a 10 variable space like x1 through 10, then maybe like a combination. So this model has multicollinearity because the x's are kind of stepping on each other's toes. They're doing the same thing in the model. We don't like that. But what we could do is we could take this multiple r squared and watch this. 1 over 1 minus r squared sub I, because that's the r squared sub I. And guess what we get? 703. Do you remember that number? There it is right there. 1 over r squared sub I. So look at the VIF of 2, and what do you notice about the VIF of 2, and what does that mean? So the variance inflation factor on variable 2, oh, didn't change it back. The variance inflation factor on variable 2 tells us what? What does this mean? How would we interpret that? Now, variance inflation is squared, so you have to watch out. If you take variance inflation, so let's put a thing, interpreting variance inflation, you want to take and square root it, because variance inflation can be used to talk about how much the standard error has been increased. But remember that variance is standard error squared. So to turn it back into what it was, we have to square root the variance inflation. Does that make sense? And Ryan, if you want to drop the question in the chat, Ryan, which one you're working on, then I can, you might be back in time, because I know you asked the chi-squared one. So maybe you might be like watching back in time. But Ryan, if you drop it in the chat, be like, oh, I'm working on the shipwreck problem, or I'm working on the gender political party, or I'm working on the preterm, post-term, all those. Kayla, what questions do you have? Because we're on open questions. What are you wondering? This model definitely has issues with multicollinearity. The x's are stepping on each other's toes. And yeah, sometimes seeing it more visually makes sense. Yeah, I know, right? I feel bad. I'm like, someone's my router. We're back to having disconnect issues because I had to reset my router. And now I'm like, okay, I feared resetting my router. I was like, watch me have disconnect issues again where we have random lag spikes. And I did it. I broke it. We're over here in cyberspace. What have I done to us? What have I done? Why are we here? Just to suffer. Ship question? Yeah, I'll do the ship question. Ship question. Let's go check out the ship question. Okay, newspaper headlines about a ship. Are you doing it by hand or are you doing it with jump? I think you're doing a jump, right? So we'll do this one with jump. We are doing the ship question. Start 201. Chapter 19. Ship question. Let's take a look, Ryan. See you tonight. Awesome. Might be doing... Should set up on like Thursday. Probably do. Maybe we'll do BS 320 review on Thursday. Yeah. Ryan, you're here live, right? We're about to do the ship question, the one you're working on. Let's take a look. Got both wrong. So you're doing the ship question, right? Let's take a look. Here we go. We're going to do the ship question. Here we go. Okay, so watch as we do the steps right here. Let's do the start of this question right here. Yeah, and I would... That's the biggest thing. The jump is going to be the number one way to solve these and get it correct. So let's do it by jump right here, because doing it by hand is a lot of work. Like, it's good practice, but we won't have to solve tons and tons and tons of values. It's going to be more work to solve by hand than it is to just solve and get the values in jump. So once again, we're doing the chi-squared test of independence. The null hypothesis having independence in it is the best way to describe it. That we'd say survival on the ship is independent of someone's gender, and there is an association, means that they are related. What are our inferences right here? Well, we have random 10%, expected cell counts greater than 5, and we need count data. So let's see right here, yes, because they are independent, not dependent. That's going with your randomness right there. Next, we get to the tougher part with the chi-squared and the p-value. So on the chi-squared right here, we need to use jump. So I'm going to do this slowly right here. Make sure you see each thing as I pointed out. Step 1, go right here and copy to clipboard. Make sure you've copied the most recent data. Sometimes working a problem multiple times, you might have old data stored. So hit Command Control C or Command C to copy that data. Now that you've got the data copied, go over to Jump and go to File, New Data Table. File, New Data Table. With File, New Data Table, you'll go into a new data sheet. Now don't click inside of it yet. From here, with it open, you want to go to Edit, Paste with Column Names. So when you paste with column names, it'll put the columns at the top of it. These are just the names of the variables you're working with. So go to Edit, Paste with Column Names. Once we go to Edit, Paste with Column Names, we now have our data inside of here. We now need to stack the data, and we're going to do that by going to Tables, Stack. Under Tables Stack, you're going to take your two blue columns, the ones that are currently quantitative, and stack them on top of each other. So make sure you go to Tables, Stack, and then you'll take the blue columns and stack them. So Tables, Stack. Double click the blue columns right here, and you'll see them appear right in here. It won't let you paste with column names. Then what you want to do is you want to write the table in the following way. Make sure to put the numbers in the right way. If you can't paste with column names, just make sure to write it in this way. So what you want to do right here is you want to go with the table you currently see, and you want to go right here and type in, you could type in outcome. And once you go right here, type in alive and dead. And then you want to go here to female. You can double click that. And then you want to go here to male. And then you want to put in the values. Does this make sense right here? How is this looking? Make sure to replicate it right here by going to a new data sheet. You just want to use the values you see in your output right here. And you want to go over here. So I'll do it this way right here. If it won't let you paste with column names, we're just going to take that table. You can double click the name of this right here and call it outcome. Then you want to put alive, dead. Then you want to call this female. You want to go here and go 385, 124. You won't put the totals in. How's this looking right here, Ryan? Is this working for you right here? Did you get the values in? How's that looking? Does it now look like this right here? How's it looking? So you should have something that looks like this. How's that looking? Good to see you, Thacker. Is it now there? Is it looking good? How's it looking? And all tables can be entered in this way. You'd want to enter in the variable name here and the variable names there. And then if it won't let you paste with column names, you can enter them all in this way. Let me know when you're there, and then I'll do the next step. Make sure you're well. Hey, good to see you here, Thacker. You'll go right there and make sure you have outcome, and then you'll make sure you have female and male. Make sure the values are correct, and you'll only enter in the values inside the table. Do not enter in the column or the row totals and the column totals. Tell me when you're there. We'll do the next step. So we have the data. We'll have the data inside a jump. We will see. And then we can get the chi-squared test statistic. We're going to stack this table next. So our goal will be, and the thing to think about, is we're analyzing two categorical variables right here, two categorical variables. And we're going to look at the relationship, whether somebody died on this ship, whether it's related to gender. And so how are we doing? And with this, good. We're going to go to table stack. Table stack. So under table stack, you want to stack the female column and the male column right there. Female and male. So tables stack, the female column, the male column. And once you've stacked this, go ahead and click OK. This is our final table right here. It's all perfectly the way we want it with the combinations of alive females. You can even check numbers right here. Alive male, check the number right there. Dead female, 124, and dead male, 1348. Make sure those numbers exist. You can edit them if there's an error. Like you could click here and edit this if there's an error. You could also enter the data in this way to start if you want, as long as you do the correct permutations of alive. So you could go across the values here, alive, alive, dead, dead, alive, alive, dead, dead, female, male, and enter in the values accordingly from reading like that. So as long as you get it entered in this way, we can now analyze it using the chi-squared test of independence. So now that we have everything entered in, if you did the stack method with the original data, you won't get outcome and label right here. Now that we have this, we're going to go here to analyze fit y by x. Analyze fit y by x. So with analyze fit y by x, we're then going to take the outcome, which is what we want to understand, put the label right here. Spoiler, it does. Spoiler, it's going to be very super significant. Great job, Madeline, right there. I like that, 100 points. And so make sure you have the reds right there. The outcome is explained by someone's label right there. And so we'll take a look at this here. If you have more questions, let me know. We're nearing the end of this one, but we can do another one, whatever you're thinking. Be like, hey, how about we work this problem? So we put the frequency, which is the count data. Those are the counts of the observations. We have the two categorical variables. This is literally condition 4 by there being count data. Those are the two categorical variables. So we've confirmed this is count data, doing chi-squared tests of independence, contingency tables, and mosaic plots. Contingency, mosaic plots. Okay, let's go ahead and click OK right here. And here's our data. And Madeline couldn't have been more right. More points, Madeline. 82.75% of males died on this ship, as opposed to with the females, only the 24.36% died. And this right here is output we sometimes give you. Understand how to read this when it comes to, especially like even row percentage right here. This is what we're looking at. It's for this row, only the females, which is the conditional distribution given someone is female. That's good information to know how to read. Just looking at a table, being like, oh, this is of the females, 75% were alive. Of the females, 24% were alive. It's a row percentage, as opposed to a column percentage. This is not pertinent to this problem, but it helps. The column percentages right here would be of the alive, because it's of the column. 57% were female. Of the dead, 91% were male. So a lot of the males, yeah, unfortunately. But the things we really need to practice calculating, which we did earlier today, are the expecteds and the cell chi-squareds, which you can also use this for other problems that have you calculate all the expecteds. You can find them this way. This problem doesn't do that, though. It does have you get the Pearson chi-squared test statistic. Yours says outcome, but mine says dash. Yep, I changed the name of it. So you can, Madeline, if you want, where it says outcome right here, you can change that to, or where yours says dash, you can actually just change this right here to whatever you want it to be. Does that make sense right there? You can double click it and call it outcome. We were making the table manually right here, so you can do this and change it. But so whatever, if you want it to be outcome, you can just double click and change the name. You don't have to, but if we're entering it in manual, I'm going to call it what it is. You could also go right here, just so we can see, and then we'll make it real quick. You could call this gender. And now when you analyze it, you're seeing if the outcome of someone on the ship is explained by their gender. So now we put in the right variable names, and now it actually says gender on the bottom. So you can double click to change those if you want. Just makes it look a little bit nicer. Madeline, great comments. Great, just like, oh, we could change that if we want. And so now we're going to go down here to the Pearson chi-squared test statistic. The Pearson chi-squared test statistic, 3-letter word, is the what of all the cell chi-squareds. The Pearson chi-squared test statistic is the what of all the cell chi-squareds. 333, 146, 101, 45. The Pearson chi-squared test statistic is the what of all the cell chi-squareds. That statistic right here, this Pearson chi-squared test statistic is the what of all these cell chi-squareds, which I'm having it display cell chi-squareds for you, is the what of all the cell chi-squareds. The Pearson chi-squared test statistic is the what of all the cell chi-squareds. The sum, exactly, Ryan, the total. And so it gives us the value. Great work right there, Ryan, 100 points. Oh, no, you're fine. Doing great. 616.48. 616.484. Does it want that extra decimal? And then something to know is this p-value for this problem is ridiculous. It's tiny. Like I will tell you this p-value. I will put it in the chat. The p-value for this problem, we got 54 jump sheets open. The p-value for this problem, 135. That's the p-value for the problem. 135 zeros after the leading zero, and then 44. So that's the p-value. So for all intents and purposes, this p-value right here, which you can see it, you'd have to zoom in. Here, I'll show you. I think I can get it so you can see it on the screen. You have to zoom in to see it. Really? You want to show it anymore? There it is. It's going to be off the screen. Oh, there it is. P-value of 4.4 e to the negative 136. And that's it in the chat if you look in the chat. That is 0. I mean, okay, nothing's 0. It approaches. It's like a limit. But for all intents and purposes, that's about as 0 can get. And so right there. And visually speaking, good to see you, Keely. Visually speaking, as Madeline was pointing out, when it comes to, is there evidence of a relationship? Evidence of an association? Yes. There is extreme evidence of an association here. We see that the relationship between whether someone lived or died is highly associated with gender, where females on this ship were more likely to live. Right here we can see of the females, 75.64% of them lived. Of the males, only 17.25% of them lived. You can find these numbers out also, and I encourage you to understand how they're found by looking at of the males, what percent of them lived. To find that, we would say there were 281 alive males out of the 1629, and that is how the number 17.2 is found. Great job, Ryan. Looks like you got it. So do understand how these numbers are being calculated right here. Like this 17.25 is of the males, which is how many males did we observe being alive out of the total males that exist. Bristol, good to see you here. So make sure to know how to solve those. Very important. Whoops, that's what happens when I click in on it. I'm going to select a wrong answer and lose the streak. So what are we going to say about this problem? Well, we're going to say that we reject the null, that the two are independent. There is very strong evidence that there is a relationship, and we did get that extra 100 right there. Got a little bit of extra time. You're welcome, Ryan. Great work. Good work. Good practice. I'm just worked through. So the chi-square is always the bigger number of the, are you talking about the jump output? In the jump output, the chi-squared is the value right here that says chi-squared. And we use the Pearson. The likelihood ratio we don't use. I haven't used it in forever. But the Pearson chi-squared is your chi-squared. The Pearson chi-squared right there, which I have highlighted in this, is the sum of all the cell chi-squareds. The other one is not calculated the same way. So the Pearson chi-squared is the sum of all the cell chi-squareds. It's not always the bigger one, though. So the Pearson chi-squared is the sum of all the cell chi-squareds. That value right there, that's the sum of all those cell chi-squareds found by observed minus expected squared over expected, which we did a full solve of this right here, and you got to deal with my horrible handwriting. But you'd have to find all your observed, which is how many people there are in each group, all your expecteds, which are row total times column total over grand totals, and then all your cell chi-squareds, and then you sum them up. And no, we don't really put problems on the test that have you do a full solve. It's just too much work. We test theory parts of it, and we test, like, can you find an expected? Can you find a cell chi-squared? So you will have to do some work finding those, but you're not going to do like finding 9 expecteds. And you do need to know how to find degrees of freedom, because Brian, solve it with me, Brian. That matrix right there is a what by what. So if you haven't done degrees of freedom, you should now do it like this for these. Chi-squared is rows minus 1 times columns minus 1. Brian, this is a what by what, and then we'll find out the degrees of freedom. So let's figure it out. Brian, that's a what by what right here. Brian, that's a what by what. So then we can figure out the degrees. Once we know it's a this by this, we can get the degrees of freedom. 2 by 2, Ryan. Great job. Since it's a 2 by 2, you simply drop each 1 by 1. 2 by 2, 1 times 1, 1 degree of freedom. Those are free points on the test. Degrees of freedom on the chi-squared is just drop. If it's a 2 by 2, drop by 1. 1 times 1, boom, done. To review, let's do a quick, maybe someone will get some help from this segment. Let's do it. Okay. Let's do a quick review of degrees of freedom because we got just a little bit more time. I'm going to grab some yogurt between class. I got Chobani. No, it's not Chobani. It's Nosa yogurt. Key lime. Some great stuff. Reviewing degrees of freedom. Explain. Okay, degrees of freedom. Let's go check this out. Degrees of freedom. Here we go. So there are 3 times you will need to know degrees of freedom. The 3 times you need to know degrees of freedom for this test are 1 sample t, 2 sample t, and chi-square. Now, there's 2 distributions at play right here. the t distribution and the chi-square distribution. So you say, well, why do I need to know the degrees of freedom? The reason you need to know the degrees of freedom is because there's infinite versions of these. The multiverse of madness at play here. Because maybe your chi-squared looks like this. Maybe your chi-squared looks like that. Maybe your t distribution looks like this. Maybe it looks like that. How do you know, put 2 letters in the chat, what your t or your chi-squared looks like? How would you know what it looks like, what shape it has, how skewed it is, or how normal it is, how peaked it is? How do you know what it looks like? It's the topic of the conversation right now. The shape of these are all determined by the what? The shape of the chi-squared, the shape of the t distribution. That was the chi-squared. Now we're back to the t. The shape of the t, the shape of the chi-squared are all determined by its what, which is the thing that controls this. The shape are all determined by the degrees of freedom. Degrees of freedom are more of a math concept. We could go into the mathematical theory, but understanding that when you know the degrees of freedom, it tells you how this distribution looks that you're working with. That's probably the most key important thing. Another key important thing about the t that I should mention here is William Gossett, good name to know, worked at Guinness Beer and created the t distribution. Fun story on that, a little time travel with Mr. T. So the t distribution and the chi-squared are the 2 distributions we're talking about here. Yep, we just did. We've done 2 versions of it. Check it out, Bristol. We're finishing. We've got the political party. Check it out. We did it earlier and we did it with Jump. Here it is right here. And we did it this morning also. So check it out, Bristol. Let me know if you have questions and we can check it out. We got it in the morning and we got it today. Good question, Bristol. Thank you. Good questions. And so now, I accidentally entered... Yeah, I believe that. Yeah, just email me, Kat. I'll fix that. So now we need to know the degrees of freedom, which I think are given to you on the formula sheet. I think it mentions them. Because you might see the degrees of freedom where it says something like... So what are the degrees of freedom for the 1 sample t? Who knows the degrees of freedom for the 1 sample t? And it could be for the t-test or the t-interval. So we're doing the 1 sample t, which is when you test 1 mean. What are the degrees of freedom? The 1 sample t is when you test 1 mean, because it's 1 sample. Might make it easy to understand if I do it this way. 1 sample means there's 1 sample. And we're testing, well, that's a mean anyways, so... 1 sample and it's a mean. It's 1 sample and it's a mean. It's a 1 sample t. So, and you might say, well, isn't there a second one? Well, that's not a sample. That's testing it against a hypothesized value. That's not a sample mean. That's a, is the sample mean equal to this? That's a hypothesized mean. So the degrees of freedom are n minus 1. And that's easy to remember because it's just 1 sample, n minus 1. Sample size minus 1, 1 sample. So that's a good one to remember. The next one is a little more complicated. That's why we usually abbreviate it, especially on the test, TDF. That's a D. I know it looks like an O. My handwriting is really bad. There we go. Best handwriting ever. So this t-test right here, or t-interval, whichever you choose to do, would be done by y bar 1 minus y bar 2. We usually assume that difference is equal to 0. Sometimes we'll put in a hypothesized value here, but let's pretend it's 0 for the moment, which is usually what we do for our test. Square root s sub 1 squared over n sub 1. This is the standard error right here. It is given to you. S sub 2 squared over n sub 2. Once again, these tests are all different to standardize, but we're here to talk about if we're doing a 2 sample. Well, then we have 2 samples, and they're both means. This is 2 sample means. T is mean, remember that. Well, the degrees of freedom here are not fun. The degrees of freedom for this problem are a little bit different. I'm going to go grab it because even I do not do this one by hand. The degrees of freedom formula for the 2 sample T are, here it is right here, copy image. Make sure we get the right image copied and, oops, really? And here we go. There it is right there. There's the degrees of freedom formula. And this is why we abbreviate it. We just write it as DF. So that whole DF thing right here, that is the whole degrees of freedom. Running to get, oh, you got it, Madeline. Rock, you got this. Keep doing great. But we also have a t degrees of freedom calculator. Look how it takes both standard deviations, both sample sizes. So if you were to solve this out, we just do it over here. Now, this is not something we do on the test, but you would enter in these right here. And funny enough, it approaches n minus 2 the closer they are to the same, but it's not always. So you can't expect it to be n minus 2, but there's kind of the highest amount it can be is total sample size minus 2. Forget that if you don't want to hear it. Remember, we say this. For the 2 sample t, the degrees of freedom formula, it's too complicated. So the first one, we're trying to put some cliff notes right here so people can memorize and understand this. The first one is n minus 1. So the second one is too complicated. So this is n minus 1. We're going to highlight these in the colors they are supposed to be. Sure. So the first one is n minus 1. The second one is too complicated. It's too complicated. The 2 sample t is too complicated. We're not going to do that. The last one, the chi-squared, which is a different distribution we're working with right here. It's used for categorical data. So the chi-squared test of independence, we are doing the following test, and we're doing the observed minus expected squared over expected, and it's the sum of these. And the reason it's called chi-squared, we're doing this in yellow. The reason it's called chi-squared, well, chi is the name of the distribution, and then you're summing up all these squared deviations and standardizing by expected. Once again, we have a difference up here divided by expected, which is how test statistics are usually found, by taking a difference up top and dividing by a standard error on the bottom. We don't really have a standard error for this, but we're dividing by the expected to standardize that difference in context of the problem. So this is the chi-squared right here. So it's got the squared on it. Good way to kind of be like, oh, it's chi-squared. And so this one's a little bit easier, I think, on the degrees of freedom, especially than the 2 sample t. The degrees of freedom for this one are going to be to do rows minus 1 minus times columns minus 1. So I abbreviate it this way right here, rows minus 1 times columns minus 1. And these are the degrees of freedom for this test. Well, what does this mean visually if these are the degrees of freedom? Well, if we were to have a matrix right here of options where there's 1, 2, 3, 4, 1, 2, 3, think about this with A, B, C, and A, B, C, D. How many degrees of freedom are there? Does anyone know how many degrees of freedom there are? There's a lot of ways to do this and a lot of ways to see it. I try not to teach every which way, so I'll teach you my first way first, and I'll show you some visuals on it that might help. The degrees of freedom for this are rows minus 1 times columns minus 1. So how many rows are there? There's 3 rows. What do we mean by the 3 rows? Well, we're talking about this right here. There's 3 rows. There's 3 possible answers to that. Answer A, answer B, answer C. And then how many columns are there? There's 4 columns. What are we talking about with the 4 columns right here? We're talking about this. So you can do the mathematics of rows minus 1 times columns minus 1, but remember, you're just dropping each one by 1. So you did have a 3 by 4, now you have a 2 by 3. So with the 2 by 3, there are 6 degrees of freedom. Another way to think about it is you're basically deleting off this and deleting off this, and your degrees of freedom are going to be this inner area here, which are 6 cells. So these are the degrees of freedom for the problem, 1, 2, 3, 4, 5, 6. And that's just a visual way to look at the degrees of freedom for this one. But with that said, we should look at some problems right here to see if we can get the degrees of freedom. At this point, you should be able to get the degrees of freedom super quick for problems like this. You want to look at it and say, Brian, this right here up top, it doesn't matter which way you say it, is a 2 by 3. If that's a 2 by 3, how many degrees of freedom are there? Well, 2 rows. If you look at the 2 rows right here, 3 columns, that's going to be drop each one by 1. 1 times 2. 2 by 3. 1 times 2. 2 degrees of freedom. Now, a common mistake that people often run into is they use the total columns as an answer to the question. Someone looks at this and say, oh, that's a 4 by 3. And we say, no, wait, you don't use the totals. There's label has 1, 2, 3 answers and 2 answers here. So that's a 3 by 2. 3 by 2, drop each one, 1 times 2, 2 degrees of freedom. We might have a more interesting one right here. That's another one. Oh, here we go. So this one right here, I'll go down to this, which is a little bit harder. We'll end off this. Does anyone know how many degrees of freedom this has? Be careful. We got the answer right below, but this is a really good check to be like, yes, it has this many degrees of freedom. 1,000 points to end the day right here. I'm going to go over and start doing some 320. Last question of the day. How many degrees of freedom does this have? Who possibly knows? Oh, Adam, no. It's all right. Adam, I'm throwing 1,000 points. Start off by saying this, Adam. You ready? Brian, that's a what by what? Brian, that's a what by what? So first confirm to me, Brian, that's a what by what? Cad, you're on the right track. I mean, Brian, that's a what by what? So I was doing 2 steps. Like double check your work, especially on the test. Brian, that's a what by what? And I'm going to confirm here once you say that answer. Cad, you did get it correct. Great job, Cad, right there. Brian, that's a what by what? Anyone know what it is? Brian, that's a what by what? Don't use the totals. Don't use the totals. They don't count as categories. Brian, that's a what by what? Who knows in the chat? Brian, that's a what by what? How many rows? How many columns? 3 by 3. 3 by 3. Reduce each one by 1. 2 times 2. 2 times 2, Cad. You said it. You got it. It is 4. Good practice right there. Make sure to, the more we practice it, the more we get it. You are given these formulas on the test, but just understanding when to use things is important. So it really comes down to just practice, 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 practice. Saying things like, Brian, that's a 3 by 3 right there. Look, 1, 2, 3, 1, 2, 3, 3 by 3, 2 times 2, degrees of freedom 4. And that's got it. With that, we'll be back. We'll be doing lots of review this week. Stay tuned. Bye for now, everyone. Bye. Good job, Kat and Adam. You got this. Madeline, good work. Losing my breath.